Yeah, so the second topic for today is the Monte Carlo approximation. So again, we've been doing this for a while, so you won't find it like too much new material, but there are some specific cases that I think we didn't get to cover. So I just want to sort of like give it as a overview, but also like a review and a little bit preview of some of the stuff that we didn't get to cover. Okay, but the topic itself, we have been using this for a while in this course. All right. So if you want to summarize your posterior distribution of, like, say, theta itself or a function of theta, in this case, let's say a particular phi function that you want to summarize, then the way that you can do it, if you want to get the expectation, is analytically, you will have to do a pretty complicated integral. Okay, so this is, if you know how to do the integral, that would be good. If not, you will have to find a way to do that. So this integral, as you can see, is we're trying to get the expectation of a function of theta. So far what we've been doing, we'll be doing theta itself, right? And now if I ask you, okay, what if I don't want to know theta itself, I want to know theta squared, what I'm going to do? Okay? So analytically, the way you should do it is you have to do, as you can see here, transformation of variable. You have to do, like, say, express, so because we're interested in this function of theta, which is phi, and then you have to express, so you know, like, so first of all, get the expectation is the random variable multiplies with the density, right? And then integrate out that unknown variable. And then do change of variable, you're able to express everything in terms of theta. But this might get very complicated to do. So this is still the function that gets you phi. And this is the posterior distribution. Okay, sometimes not easy to do. So generically, we try not to do it too much. We usually try to do simulations to approximate that. And then this type of simulation that we do is called Monte Carlo approximation. Right. So the procedure, we've been doing this so many times now, so you might find it pretty familiar. What you do is you typically generate large number of samples from its posterior. So this is still working on theta, right? And then if you want to get like the mean of theta, for example, I'm just going to take the average of all of the draws that I have. Okay, that's what we've been doing. Okay, and one step further, if you're curious in the function of theta, which is what we were talking about, say if it's, remember it's phi as a function. If I want to know the mean of phi, then what you can do is you just do one step further, that you not only have a bunch of draws, so you first of all have a bunch of draws about theta, right? And then because of this relationship, you can get a bunch of draws for phi. And then if you take the average, that will be a good approximation to the analytic solution. Okay, so this is the basic, basic theory foundation that we've been using, based on which that we've been using Monte Carlo approximation. Okay. All right, so this hope is intuitive enough. And then, of course, you can summarize things in various ways. And in short, remember, like, say, the means, the variance, quantiles, any kinds of functions. As long as you can do that on the unknown parameter from its posterior, any kind of functions of that, you're able to do it. Okay, so this is something new, I should say, that we never covered, because so far we'll be just talking about theta itself. Like in the beta binomial case, we're just talking about the unknown parameter p, right? We do any kind of summaries of that. And then in the normal as well as gamma normal, we've been just talking about getting to know about the unknown parameter directly. But of course, if you want to know specific function about theta, then Monte Carlo approximation probably will be the only way that I can do, because over there the analytic solution will be too complicated, like what I showed at the beginning. So the example Okay, so this is just a quick, actually, this is a review that we did so far, that if I only just care about the unknown parameter, I can do exact solution and approximation. Okay, so this is what we saw before. And S, which is the number of draws that you do, determines the accuracy. Okay. Usually 1,000 is enough, especially for simple model like what we do. And then later, if you have more complicated models, you might have to do a lot more draws to do that. This is what we saw. And then what if you have functions of theta? So this is the new material in this supplementary material. So theta, if in the beta binomial case, if we're looking at p, which is the unknown proportion, a lot of times people are not only interested in the proportion p, they're also interested in something called odds. So odds is the ratio of the likelihood of something happening over the likelihood of something not happening. Okay. So as you can see, what I define here, O stands for odds. It's the ratio of the probability of happening, which is P, over the probability of something not happening, which is 1 minus P. Okay, so this becomes a function of P, right? So this is a function of P. And if you want to do it in the analytic way, say I want to summarize the odds, which is unknown, and it's linked to the proportion parameter P, then what you do, remember we did the review in the introductory material, the lecture, talking about like change of variable, and then you have to show like all of the, like say you have to compute this, and that goes into all of the computation. Okay, so this, again, might not be something that you'll be able to recognize. We don't really cover that in this course anyway. So instead of doing the exact solution, since now we just have a function of P, and then we can simulate a bunch of P's already from its posterior, then we just need to do this one more step to simulate more O, in this case, which is the odds. Okay? So the Monte Carlo approximation, so this is sample code. So the first 3 lines are what we did before. Okay, you set C, so you can make your results reproducible. You set the number of samples you want to do. So here I'm still doing 1,000. And then we create a vector called beta samples. I'm doing 1,000 of them with the posterior parameters. Remember this 15.0, 15.06, and then for 10.56. And then I have a new vector, as you can see here. That is pretty straightforward because I told you that R can do this vector manipulation pretty easily. So I have a vector. 1 minus that vector will just get 1 minus P, like as a vector. And then I just use this division sign here. It's going to do element by element. Okay? So this odds is a vector of length capital S. Okay? And each is one draw of P over 1 minus P. Okay? So when you do that, you're going to have a vector of length S, which is, like we name it as odds. So you get 1,000, in this case, draws of odds directly. Okay. So as you can see that, you first of all get the draws from its posterior. That's the draws for the parameter. And then whatever function that you apply to the parameter, you can pretty much very straightforwardly generate them using the definition, whatever the function is. In this case, is the odds. All right, so now you might be wondering, okay, how am I supposed to summarize the odds? So again, we ended up with a vector of 1,000 draws of odds. So in order to summarize it, not surprisingly, you just do whatever that you're curious about. For example, if you use the mean function, you will get a good approximation to the mean of the odds. The median, so available function. And then also if you want to get a 95%, so this is a demo of a 95%, middle 95% credible interval, you can get that as well. Okay. So this, I hope, opens up your understanding about Monte Carlo approximation, that a lot of times, so far what we see before this lecture, what we saw is if you have the known distribution for the posterior, if you don't want to use analytic solution, you can use Monte Carlo approximation to approximate it, okay? By doing like R gamma, R beta, R norm, whatever you can think of, right? But that still, we're still talking about the unknown parameter. Sometimes people want to know more about the unknown parameter. So it's not only about the parameter itself, but about functions of parameter. A typical example, like what I presented here, is the odds. Okay? It's p over 1 minus p. So that becomes a function. Analytic solution too daunting to do. The integration will be too hard to do. So we usually just don't worry about that at all. We move to Monte Carlo approximation. And the way to do it is you still get the unknown parameter draws from whatever posterior you have, and then do one more step to generate draws of the new functions of the draws. Okay, so that's what you can do if you have a function about the unknown parameter. Okay. So this is one new use of Monte Carlo approximation. Another thing I want to cover is so far we've been working with just one sample, especially with the beta binomial case, right? We just have one sample and then we try to summarize that. Sometimes you might have multiple. And then say in this case, suppose we get data from a particular disease, like the cases of failures from a VA hospital, and then we have 2 years in a row of the data. Okay. So each year, you have a number of patients, which is N1 and N2, and then the number of cases, which is real failures, Y1 and Y2. Okay. So now you have these two. Especially some people might be wondering, okay, how can I compare this to, especially if I want to know, say in this case, this is a binomial density, right? Like it's how many success sort of out of the number of trials that you have. So naturally, you might want to make inference about the unknown P. In this case, it's P1 and P2 because you have 2 of them separately, right? And then a lot of times, if you get inference for P1 and P2 separately, some people might want to compare which one is better, right? So this, again, will be a case that if you try to get the analytic solution, will be really complicated to do, but simulation can help us a lot here. The general idea is that if you look at this, I'm going to show you the procedure in a minute, but just think about the general picture that you have data from for 1992, and then you have your P1, you do all of the inference, and then you get, say, you put a prior on that, you get a posterior, and then you can get a bunch of draws from the R beta function that we know, right? So get a vector of that, for example. And then for the data in 1993, you do the same. So you put a prior, and then you get the posterior, and then you can get a bunch of draws as well, right? So the good thing about doing Monte Carlo approximation is there's theory to back up that if you directly compare those two vectors and you summarize from there, you might be able, like you have a good approximation to the real difference between P1 and P2. Okay. All right, so let me just show you what I mean. So I guess I'm using theta 1 and theta 2, sorry, but it's the same thing. So here we're putting 2 independent prior, like it's 2 independent binomial models, right? And then we put 2 priors separately for it. And I'm putting a uniform prior, which is beta 1, 1, just to start simple. We don't know what it is, so I just put a very little informative prior. And then we come to do the regular analysis that we do. You're going to come to the posterior for theta 1, and then posterior for theta 2. Okay? So use those for like 2 sets of numbers for now. And one thing very important is to notice that we're assuming independence along the way. Okay? The data are treated as independent from 2 years. And the priors, we give beta 1, 1 for both, but it's still considered as independent. So the parameters themselves are independent from each other. So you see that I wrote here and there. So keep in mind that this is a model that we don't assume any kind of dependence between the two. So we can just do the 2 posterior analysis totally separately. Okay, one for 1992 and the other for 1993. So the task like I said earlier, is how to compare theta 1 and theta 2. Because theta 1 is the success proportion for 1992, and theta 2 is the success proportion for 1993, right? And here, success, I mean, is really failures because it's the number of cases happening. So a natural question to ask will be, okay, from 1992 to 1993, do you think, say, like the treatment is improved at all? Right? And then the treatment can be, I mean, this question can be rephrased as comparing theta 1 and theta 2 to see which one is larger, right? Ideally, we want to see what? Theta 1, like theta 2 to be smaller, right? So that means you have some improvement in the treatment that you're doing from 1992 to 1993. Because theta 1 is the proportion of having like real failures, theta 2 as well for 1993, so you want to see a drop. Okay, so in this context, it's a drop. So I show you really complicated to do analytic solution, so I just want to get you, I need to do it over here, yeah. So we define this difference, theta 2 minus theta 1, I should say, in the way that we set it up, to be delta. And this delta, again, becomes a function of theta 1 and theta 2, right? So for theta 1 itself, we know what to do. You can do draws, you can do posterior summary for theta 2 as well. And we treat them totally separately. So now, if we define delta, which is looking at the proportion difference of the second year to the first year, then this is a function of theta 1 and theta 2, right? And like we talked about so far, as a function, it will be much easier if you can do it in Monte Carlo approximation. And so this slide on top, we don't get into detail, but I do want to show you that to get the mean, to get the variance, and then all of that can only just give you a pretty rough inference. But if you can directly summarize whatever you have for theta 2, the draws that you have, and then the draws that you have for theta 1, and then you will be able to get a good approximation about this delta, which is the difference between these two, which is the parameter of interest in this particular inferential question. Okay, make sense? All right, so by that idea, then everything flows pretty smoothly. I have whatever my draws for theta 1. So let me see here. So theta 1s is from a beta distribution. These are all of the parameters, and then the data from 1992, right? And then these are all from 1991. And then from there, I define the difference. So I get a vector of this, a vector of this, and then I can get a vector of the difference. Okay? And then in order to see how many of them are, like say, the probability, posterior probability that theta is negative, what I can do is I can just summarize how many of the difference is smaller than 0. So this, again, this is a logical operator, right? So you get a bunch of true and false. If you sum, you're summing, like you're counting how many is true, right? And then divided by the total number of simulations that you do, you're going to get an approximated posterior probability. And it's roughly 95%. So what we can say is, if we think about the difference of theta 2 and theta 1, we define that as the new unknown parameter, which in turn is a function of theta 1 and theta 2. We can use Monte Carlo approximation to get an approximation to the posterior probability of that, which is 95%. Right? So this is saying that 95%, we have 95% posterior probability that there is a decrease in the ratio, or I should say in the proportions of the real failures for that particular disease. Okay. So this again is a new use of Monte Carlo approximation that we didn't get to talk about. So far, I mean, previously we've been focusing just on one set of data, for example. But now, as you can see, for one set of data, if instead of thinking about the unknown parameter itself, you want to know functions of the unknown parameter, like the odds, then you can do Monte Carlo approximation. Okay, it's just one more step of simulation. Sometimes you have multiple data sets to compare to. In this case, it's both of this are independent. They're beta binomial model that we dealt with before. And then what's left for you to do, if you want to know the difference between these two, then you can define this new parameter, unknown, which is delta. It's theta 2 minus theta 1. And then analytic solution is too complicated to do, but you can go for approximation. And the way that you do for the approximation is you do them separately because we assume them independent to start with. So you're going to get a vector draws of theta 1, a vector draws of theta 2, take their difference, and then summarize that. And then that gives you a good enough approximation to the analytic solution. Okay. Cool. So these are some new uses, but again, everything follows from what we saw before in Monte Carlo approximation. But I do hope that this supplementary material gives you new ideas of what you can do with Monte Carlo approximation. Okay. Any more questions? All right. If not, I think we have 15 minutes. I'm just going to walk around to answer any questions you might have. I guess because lab 2 is due on Thursday, so that's the stuff that I